Hi everybody, welcome back to Lafayette Systems. Today's video is going to be a little bit different. This is a Q&A video celebrating 50,000 subscribers. So I did not expect to get this many subscribers, and I'm extremely humbled by all the people who have found these types of rocket projects interesting. So I wanted to spend a little bit of time answering some of the questions that you guys left on the community post that I posted about after getting 50K subs, and also answering some of the questions that I often see in my email. So the first question is, what do I do for my day job? I mentioned earlier that I work full-time, and all of this stuff are just things that I do on the side as kind of hobbies. So I work for the United States government as an engineer. I work on all sorts of really cool stuff. You probably won't see videos of most of those, but I'm having a great time doing that. It's a super, super rewarding job, and I get to do things that I never really would have expected to be able to do. Some of that job relates to the things that I do here, kind of aerospace engineering, working with rockets and doing guidance, navigation, and control things. Other parts of that job are just PowerPoint, which actually also feeds into the Lafayette Systems channel because I do all of my animations for this channel in PowerPoint, mostly because that's the only kind of animation tool that I really know how to use. But again, all of these things you see on the channel are just side projects that I do in my spare time. And my work keeps me pretty busy and sometimes makes me travel for long periods of time. So sometimes you guys will see large gaps between when I release videos. I try to minimize those as much as possible. I don't really have like a release schedule. I try to do about once a month, but sometimes I'm overseas, and so I can't always put together videos on schedule. The second question is about what is the goal of my channel? Why do I do these things? Do I have some kind of end goal I'm going towards, or are these just things that I come up with and then I see if I can do them? My channel doesn't really have like a goal I'm working towards. I just kind of make cool stuff. I try to make my projects more complex, and I try to learn new things with each one. So I've done single stage rockets, I've done two stage rockets, and you guys will see the first video of a two-stage flight on this channel coming up pretty shortly. That one's kind of a bummer. Don't mean to spoil it. But then as I go forwards, I want to make my rockets bigger. I want to make them go faster. And then with Hatchet, I'm trying to do drone stuff. I've done a little bit of RC planes in the past, but this is the first kind of foray into drone manufacturing that I've ever done. So I'm looking forward to that. But no, there's no end goal here. I'm not trying to demonstrate some kind of capability. I'm not trying to produce some fancy system. I just find a cool project and I try to do it. And just sometimes those projects take a really long time. Next up is, are you going to be making any control systems for more complex rockets like liquids? I do not have plans to do any liquid rockets in the near future. Liquids are really hard, and it's also very difficult to like work on those and test them just like in my house, even for the pretty stable kind of combinations of fuels and oxidizers. A lot of the liquids do things like nitrous oxide or alcohol with liquid oxygen. I don't really want to be having large quantities of any of those chemicals around. They're just fire hazards and they're dangerous. I do want to do more complicated control systems for solid fueled rockets. So I want to do thrust vane control, I want to do thrust vector control, and then I want to do attitude control with fixed solid rocket motors. Those are all goals that I have. I don't really have a specific order I want to do those in, but you hopefully will see some larger projects on this channel that will include some of those more complicated types of control structures in the future. Next up, what was my motivation to do rocketry in the first place and to do active control rocketry specifically? So I did rocketry when I was a little kid. I would build little Estes rockets with my dad, and we'd go shoot them off. I got into college and I watched some BPS space videos, and I also watched this one video from a guy who made a canard controlled rocket. It was a really rudimentary one, and he said it took him like a week to do it, and I was like, oh, well, I should do that. And then I went down a rabbit hole and spent like 3 years trying to make canard-controlled rockets work really reliably and work successfully. I had kind of marginal success there, and that is what got me into aerodynamic control of rockets, and I've been there ever since. Active control systems are really cool, and it leverages some of the things that I learned in undergrad and in grad school. And so it's been a really interesting journey taking the academic things that I learned and trying to implement them in real life, because schools don't often do a very good job, at least in my experience, of giving you practical experience implementing the things that you're learning in a classroom. So this has been a really useful hobby for me in doing just that. Next up is what did I study and how did I learn all of the stuff that I use in this channel? So I studied astronautical engineering in undergrad, which is mostly about space vehicle control and rocketry and stuff like that. And some of that experience has helped me a lot. The biggest thing that helped me was the math background. So I learned a lot of really complicated things about how spacecraft control themselves, and to be honest, has not generally come in that handy doing hobby scale stuff like this. But all of the math background has, taking intro to control classes really helped understand what PID is even doing and why do we use it. And also classes on rocketry, so rocket propulsion, how rocket motors work, how we characterize them. But probably the biggest skill that taught me was just the math background. It turns out if you know how to do a certain subset of math, a lot of stuff becomes way easier. And so I'm very fortunate that I had that experience. And then I did grad school, I did mechanical engineering. A lot of that experience just taught me how to learn new things by myself. So undergrad's very good at stepping you through a bunch of classes in a very formal way. Grad school, you're very kind of left to your own devices in a way. And so that was a really useful experience in teaching me that you can just go learn stuff. Like you don't need a class for it. You can just Google stuff. You can actually just buy textbooks and just try to learn them that way. And if you have particularly the math background, the buying textbooks and teaching yourself, I have found to be a pretty useful technique for me. That being said, I don't think you need any specific educational background to do active controls. There's lots of people that don't have a formal engineering background who are doing rocketry in general or active controls in particular, and a lot of these guys do a better job than I do. So you can just learn everything you need to know to do any of these projects by yourself. A lot of times it's difficult to figure out where to start learning, but all of the resources are available generally for free on the internet, which is it's a pretty wild world to live in, that you can just learn, crazy new skills in your free time by yourself, and you don't need to pay tens or hundreds of thousands of dollars to go to university to do it. So along those lines, what resources did I use when I was first learning, and what resources do I usually use now? A follow-on question for this is, what books do I use? So first, for resources for electronic design, this is the primary flight computer for Diamond X and for a couple of follow-on projects that you're going to see. I learned electronic design totally on my own. So I didn't really have any formal background in that from an educational standpoint. So the resources I found useful are Altium Academy, who I'll link, PhilsLab, who's a great resource, and then I would just Google circuit design for specific types of circuits. So I would Google, how do you do reverse voltage protection? There are also lots of good textbooks out there. My trick for getting textbooks is lots of times textbook manufacturers will make new editions of a textbook every year, mostly so that they can sell more of them, but also they'll change the homework problems in the back, so it's harder for students to take the answers from previous years. So they'll change the questions in the textbook, but the 15th edition of circuit design is going to be almost identical to the 14th edition of circuit design. So if you find a good textbook you like on Amazon or another online store, you can look for a couple generations back or a couple editions previously, and they're generally way cheaper because students can't use them for homework assignments. The homework problems have changed, but the fundamental, content of the textbook is no different. A lot of times those are way cheaper than the newest, most up-to-date version. In terms of book resources, there's a couple books that I'll show you here that I have found really useful, especially when I was first starting out. So this is the first book that I found really useful. It is Rocket Propulsion Elements. This is the 9th edition. There are a couple previous ones that are just as fine too. And this book is a textbook, but it's got all sorts of really good stuff on all different types of engines. This one is really good at showing you kind of the trade space for different types of propulsion. So this talks about all the different types of ways spacecraft can control themselves and what the trade-offs between them are. There's also these really great plots that show you the performance differences in liquid propellants. Shows you different types of propellant designs and different types of engine designs. And this is a really great resource for me to learn how all the different types of rocket propulsion systems work. Not so much in a practical sense, like I'm not going to go build a pressure-fed liquid-fueled engine, but that background is always really useful to have. It also has a great chapter on solid rocket propellants. So for me, I just use it as background for how solid rocket motors work. But if you want to design and build your own solid rocket motors, this is a really good resource for understanding the burn rate equations, what the different parameters inside of the burn rate equations are, and how you can characterize them from real tests. Next up, Introduction to Aeronautics, a Design Perspective by Stephen A. Brandt. This was the textbook for my Intro to Aeronautical Engineering class in undergrad. It is super duper useful. It has things like the basic lift and drag equations for airfoils and then wings and then full aircraft. This was really useful when I was trying to predict the lift and drag forces on rockets. It also has a bunch of material on how you correct for and adjust your control system for effects of different Mach numbers. And it talks about how all the different equations for lift and drag change at various different sub, trans, and supersonic regimes. So this graph in particular was very useful. This is adjustments of the lift curve slope, CL alpha, through the different Mach numbers. So for my rockets, I had to use different equations for subsonic and supersonic CL alpha, and then I had to do a little bit of interpolation between those two because both of those equations yield infinity at Mach equals 1. So this has a ton of really good background, mostly in predicting the lift forces that wings will generate, and that has been very useful for me. If you want to design aircraft, even drones, there's also lots of really good stuff on sizing. So that's some of the initial math you'll do to figure out, I want to bring a certain amount of payload, carry it a certain distance using a certain type of propulsion. These equations will tell you how large the aircraft needs to be and will help you figure out how to balance like weight and size and wingspan and wing area, things like that. Next up, Tactical and Strategic Missile Guidance and Introduction, Volume 1. This is probably the most useful book I've had for active control systems. This is actually these two, and we're going to see some more, are from the AIAA. That's the American Institute of Aeronautics and Astronautics. So there, you can just buy them on Amazon. This book has all sorts of really good stuff on different types of guidance modes. So this is proportional navigation. There's stuff about strategic missile guidance, so intercepting ballistic targets, all sorts of crazy stuff. Semi-active laser-guided rockets and missiles, so SACLOS guidance. It also has a lot of math on how you compute miss distances and all sorts of stuff. This has been really useful background for me when I'm designing guidance systems in particular. So you guys are probably looking at that word and asking some questions. It turns out that the guidance systems that you use for weapons are typically almost identical to the types of guidance systems you'll use for just regular rockets, airplanes, even airliners, right? So how cruise missiles steer is basically the same way that airliners steer. This is a really good book specifically for rockets because it turns out a lot of the airplane equations don't make a whole lot of sense for rockets who are symmetrical on different axes. This book also has a lot of really interesting stuff on how to kind of characterize and tune guidance and control systems, and includes both MATLAB code and also full block diagrams for full like 3-loop autopilots, which I found really useful when I was trying to figure out for the first time how all of this stuff all works together. So if you're trying to get into active control systems and don't really know where to start, just the Wikipedia page for the PID system is a great one, but also this book is a really useful tool, mostly for GWiz stuff, but it also gives you a lot of like introduction MATLAB code and the block diagrams that will be really useful when you're trying to start simulating rockets flying around. Next up, Advanced Tactical and Strategic Missile Guidance. This is part 2 of the previous book. They're in a series. This one I have found less useful, but super cool. This one includes a lot of things for like how you start simulating rockets, what the equations of motion of a rocket are. This is an estimation of the lift coefficient of a rocket, just based on its size and wing shape and nose cone length, things like that. So this is a great resource if you want to start coding those simulation tools like the ones that I showed off in the last video. This one, obviously being advanced, includes some more interesting stuff. So this is modern control and autopilot design, and again includes a bunch of really great MATLAB code so that you can start simulating this stuff all by yourself. Some of it will not be super useful. This is talking about how you can properly track and include in the guidance law targets that are moving. When I fly Diamond X, those targets obviously are sitting still. They're just regular GPS coordinates. However, one cool thing is that, for the guidance math, having your target move or having your rocket get pushed off course by a gust of wind are the same thing. So if you know, because you found it in a cool textbook, that your rocket can handle a moving target really well, that also means that your rocket can handle getting pushed around by wind or having weird nonlinear aero effects happen to it really well also. So some of this stuff you'll find useful, some of it, probably not. But nonetheless, this is a really cool book. Shows you all the crazy math that weapon systems use to try to guide themselves very precisely. Next up, optimal control theory with aerospace applications. So optimal control theory is a subset of control theory where your system, in this case the THAAD interceptor, is not just trying to get from point A to point B, but it's trying to get there the best possible way, whether that is minimizing energy loss or maximizing energy at intercept, whatever it is. The math behind optimal control theory can get a little weird, and some of the other resources that I've found don't do a good way of letting you apply the optimal control theory in a normal way. But this book does a pretty good job. It walks you through the math pretty easily, and it's got some cool charts in it. I haven't used a lot of this stuff in my hobby work, but nonetheless, it is probably a good resource if you wanted to get into the fancier control theory type stuff. The last great resource I have is the Ben Dickinson YouTube channel. So I actually met him recently. He's a really cool guy. He does really great guidance, navigation, and control videos. His videos really helped me in my undergrad courses in control theory. He's got really well put together videos with great plots, and goes through some of the really specific but also really important types of guidance and control that are useful for missile and rocket design and also airplanes. He's got a great series on proportional navigation, which is the basis, it turns out, for a lot of different guidance laws. And then he's also got other ones on autopilots and the types of circumstances where autopilots might start to diverge and how you can fix that. So I can't recommend his channel enough. He walks through, examples of guidance and control really, really well. So if you're interested in this kind of stuff, I would highly recommend checking him out. Next question. Can I buy your rockets, or can I buy the STLs, or where are the STLs available? So I try to make this clear in the descriptions of my video, but I do not supply the STLs for any of the flight versions of my rocket. Export control laws are vague on the subject, and I try to steer well clear of any export control problems. If you are a channel member, though, you can access models like this that I have kind of poorly painted. This is just the outer mold line of Diamond X Block 2. So you can download these and print them yourself. Again, they're just the outer mold line, so there's no internal structure here. But nonetheless, if you want little desk models, that's a really good resource. I also don't sell completed rockets. I actually think you guys would be surprised how useless they are to most applications. My rockets have a really convoluted set of ground control software and flight software that they need to work. They're not fieldable systems that you can use for research or other purposes. So if I did, it really wouldn't be that helpful to you. But nonetheless, I don't sell rockets. These ones are just, I just make them for myself, and I retain all of that kind of intellectual property internally. But I do encourage you to kind of use these as inspirations or examples of things that do work if you guys want to start active control projects. I think a lot of the fun is in designing something and experimenting with things yourself. And I found it very rewarding not to just make things that other people have made, but to try my own way and try to do things that nobody's done before. So I hope that these projects serve as an inspiration, but again, I'm not packaging them together and providing them to anybody as a fieldable system. Last question, most important one. I've got this one many times. It is, where is Momo, and does he know any tricks? Buddy, we have to do tricks now. Ha! Here he is. Stay. Do not, no, Momo, don't escape. You like this? Momo. All right, Momo, are you ready to do your tricks? You have to earn these ones, okay? Momo, sit. That's a good boy, good boy. I have to reload here. Good boy. Momo, paw. Wrong one. And we have to hold hands. There we go. He does not like holding hands, but he has to. All right, buddy. Ready? Other paw. Yeah, good boy. Good boy. All right, Momo. Last one. I gotta find it. There it is. Ugh. Okay. All right, Momo. Last one. Ready? Up. Momo, up. Yeah, you got off the ground. Good boy. So those are all the tricks that Momo knows. I've tried to teach him new ones, and his brain is full. So he's just going to know those 4. But honestly, buddy, for an orange one, I think you're doing pretty good. So that's all the questions I had for the Q&A. I really appreciate you guys sticking it out to the end, and we'll see you in the next one. Right, buddy?